The Big Bang was not an explosion. And I know what you're thinking, but it's called the Big Bang. How can it not be an explosion? Well, that name was actually given to it by a fellow named Fred Hoyle in 1949, and he was trying to make fun of it. He thought the whole idea was ridiculous, so he called it this silly name on a radio broadcast, and wouldn't you know it, the name stuck. So now we're stuck with this name that makes everybody think the wrong thing. Now, what's an explosion? Think about what happens when you have a bomb or a firecracker. You've got this thing sitting in space, and inside it there's tremendous pressure and heat compared to the outside. The pressure difference is what makes it go bang, and material rushes outward into the space that was already there. The stuff inside moves through space at high speed. That's an explosion. The key thing here is that the space already existed. The bomb explodes into something. There's a center where the bomb was, and the debris flies outward from that center. If you were far enough away and looked back, you could see the empty center and the expanding shell of material. You could say, aha, the explosion happened over there. But the Big Bang wasn't like that at all. There was no center. There was no outside for it to explode into. In fact, there was no space for anything to explode into because space itself didn't exist yet. You see, and this is the crucial part, the Big Bang wasn't an explosion in space. It was an expansion of space itself. Now, what does that mean? Let me try to help you picture this. Although I have to warn you, it's not easy to picture because we don't have any everyday experience with space itself expanding. We're used to things moving through space, not space itself getting bigger. Imagine you've got a balloon, and on the surface of this balloon you draw some dots. Now forget about the inside of the balloon and forget about the outside of the balloon. I only want you to think about the surface. You're a little two-dimensional creature living on the surface of this balloon. And as far as you're concerned, that surface is all there is. There's no inside or outside in your universe. Now somebody starts blowing up the balloon. What happens to those dots? They move away from each other, right? But here's the important thing. None of the dots is at the center of the expansion. Each dot sees all the other dots moving away from it. If you're standing on one dot and you look around, every other dot is getting farther away. And the dots that are farther away from you are moving away faster than the nearby ones. That's what's happening with our universe. Space itself is stretching, getting bigger, and as it does, everything in it gets farther apart from everything else. Galaxies aren't flying through space away from some central point. Space is expanding, carrying the galaxies along with it. Now you might ask, well, what's it expanding into? And that's a perfectly natural question, but it doesn't have an answer. Or rather, the question doesn't quite make sense. The universe, all of space, isn't expanding into anything. It's just getting bigger. I know that sounds strange, but that's what the mathematics tells us, and that's what the observations show us. When we look out into space with our telescopes, we see galaxies in every direction. We don't see an empty center with galaxies on the edge. We don't see ourselves on the edge looking inward at all the galaxies. Everywhere we look, there are galaxies, and they're all moving away from us, not because we're special or at the center, but because space itself is expanding everywhere. Here's another way to think about it. Imagine you have a rubber sheet with a bunch of coins on it. If you stretch the rubber sheet, the coins get farther apart. But notice, there's no center to this stretching if you imagine the rubber sheet going on forever in all directions. Every coin sees every other coin moving away from it. That's what's happening with space. Now let me tell you why an explosion is completely the wrong picture. In an explosion, things are hot and under pressure in the center, and they rush outward into cooler, lower pressure surroundings. The temperature difference and pressure difference drive the explosion. But in the early universe, there was no cooler outside. The whole universe was hot. Everywhere you could go was the same temperature, roughly speaking. There was no pressure difference because there was nowhere for anything to rush into. And here's another important difference. In an explosion, the stuff flying outward has a speed. It's moving fast, maybe, but it has some definite speed, and that speed can't be faster than light. But in the expansion of space, there's no such limit. Distant galaxies can be moving away from us faster than the speed of light, and there's nothing wrong with that. They're not moving through space faster than light. Space itself is expanding, carrying them along, and there's no speed limit on that. You see, Einstein told us that nothing can move through space faster than light. That's absolutely right. But he said nothing about space itself expanding. In fact, his equations of general relativity, which tell us how space and time work, they allow space to expand at any rate it wants. Now let me tell you what we actually know about the early universe, because this is beautiful stuff. If we run the expansion backward in time, we find that the universe was smaller in the past. If it was smaller, everything was closer together. If everything was closer together, it was denser. And if it was denser, it was hotter. So as we go back in time, the universe gets smaller, denser, and hotter. About 13.8 billion years ago, the universe was incredibly hot and incredibly dense. Not dense in one spot, but dense everywhere. Every point in space was essentially the same as every other point. Hot, dense, and expanding rapidly. How do we know this? Well, one of the most beautiful pieces of evidence is something called the cosmic microwave background radiation. Let me tell you about this because it's a wonderful story. In the 1960s, there were two fellows, Penzias and Wilson, working at Bell Labs with a big horn-shaped antenna. They were trying to measure radio waves from space, but they kept getting this annoying hiss, this static that wouldn't go away. They checked everything. They pointed the antenna in different directions. They even found some pigeons nesting in the antenna and cleaned out all the pigeon droppings, thinking maybe that was the problem. But the noise was still there. Meanwhile, just a few miles away at Princeton University, there was a group of physicists who had been thinking about what the early universe should look like. They realized that if the universe started out very hot and dense, it should still be filled with radiation cooled down over billions of years of expansion. They were actually planning to build an antenna to look for this radiation. Well, somebody told Penzias and Wilson about this work at Princeton, and they realized, wait a minute, this noise we've been trying to get rid of, this is it. This is the radiation from the hot early universe. And they were right. They discovered the afterglow of the Big Bang, the cosmic microwave background radiation. This radiation comes from everywhere in the sky. It's the same in every direction, which tells us that the early universe was the same everywhere. There was no center where the explosion happened. It happened everywhere, all at once. When this radiation was released, the universe was about 380,000 years old, and it had a temperature of about 3,000 degrees, hot enough to glow. But since then, the universe has expanded by a factor of about 1,000. And when space expands, it stretches out the light traveling through it. The wavelengths get longer, the energy gets lower, the temperature drops. Today, that same radiation has been stretched out so much that it's in the microwave part of the spectrum, and it corresponds to a temperature of about 2.7 degrees above absolute zero. That's incredibly cold, but it's there, filling all of space, the same in every direction. This is smoking gun evidence, you might say, that the universe was once very hot and very dense. And more than that, the tiny variations in this radiation, little hot spots and cold spots, they tell us about tiny density differences in the early universe that later grew into galaxies and clusters of galaxies. It's a baby picture of the universe. Now, I want to come back to this business about what the Big Bang actually was. We've talked about what it wasn't, an explosion, but what was it? Well, honestly, we don't fully understand what happened at the very beginning. The mathematics breaks down when we try to go back to what we call time zero. What we can say is this. At some point, roughly 13.8 billion years ago, the universe was in an extremely hot, dense state, and space was expanding very rapidly. We call this the hot Big Bang era. How did it get into that state? We don't know for sure. There are ideas like cosmic inflation, which suggests there was an even earlier period where space expanded even faster. But we're still working on understanding all this. The important thing is that this wasn't happening in one location. It was happening everywhere. Every point in space was part of the Big Bang. If you could go back in time and be there, you wouldn't see the Big Bang happening over there somewhere. You'd be in it. It would be all around you. And there's something else that confuses people. They ask, if the Big Bang happened everywhere and the universe is expanding, does that mean the universe is infinite? And the answer is, we don't know. It might be infinite. It might be finite but have no edge, like the surface of a sphere has no edge even though it's finite in size. We don't know what the total size of the universe is. We can only see out to a certain distance, what we call the observable universe. And beyond that, we simply don't know. Here's what we do know. The universe is expanding. Every galaxy we can see, except for a few very nearby ones held together by gravity, is moving away from us. The farther away a galaxy is, the faster it's moving away. This relationship was discovered by Edwin Hubble in 1929, and it's one of the great discoveries in all of science. And the expansion is actually speeding up. About 5 or 6 billion years ago, something started making the expansion accelerate. We call this mysterious something dark energy, but we don't really know what it is. It seems to be a property of space itself, and it's pushing the universe to expand faster and faster. So you see, when you really understand what the Big Bang was, it's much stranger and much more interesting than any explosion could be. An explosion is easy to picture, sure, but it's wrong. The real story, the expansion of space itself, carrying everything along with it, with no center and no edge, that's harder to picture, but it's what actually happened. And this is what I love about physics. The universe doesn't care about what's easy for us to imagine. It does what it does according to its own laws. And our job is to figure out what those laws are and follow them wherever they lead, even if they lead us to ideas that seem strange or counterintuitive. People sometimes ask me, how can you be sure about all this? You weren't there. Nobody was there. And that's true. But we can see the evidence. We can see the galaxies moving apart. We can detect the cosmic microwave background radiation. We can measure the abundances of the light elements, hydrogen and helium, and they match exactly what we'd predict from a hot, dense early universe. We can look at the large-scale structure of galaxies and see that it matches the pattern we'd expect from those tiny fluctuations in the early universe. All of this fits together into one coherent picture. That's how science works. We make a hypothesis about how nature works, we figure out what that hypothesis predicts, and then we go look to see if those predictions match reality. When they do, again and again in different ways, we start to have confidence that we're on the right track. But we also have to stay humble. There's still so much we don't understand. We don't know what dark matter is. We don't know what dark energy is. We don't know exactly what happened in the first tiny fraction of a second after the universe began. We don't know if the universe is infinite or finite. We don't know if there are other universes. These are things we're working on. This is what makes physics exciting. We've learned an enormous amount, but there's always more to discover, always deeper questions to ask. So, when somebody tells you the Big Bang was an explosion, you can tell them, no, it wasn't. It was something much more interesting. It was the expansion of space itself, starting from an incredibly hot, dense state with no center and no edge, creating the universe as we know it. And if they look confused, well, that's okay. It is confusing. It should be confusing. The universe is under no obligation to make sense to us, but that's what makes it so wonderful to try to understand it. The name Big Bang is a bit of a joke that became permanent, but the reality it describes is no joke at all. It's one of the most profound insights we've ever had about the nature of reality. Not an explosion, but an expansion. Not something happening in space, but space itself coming into existence and growing. That's the real story, and it's more amazing than any explosion could ever be.